Hello everyone, welcome to today's data learning talk. So today we're very happy to have Yi Zhou from Adobe Research, and she will talk about fully convolutional mesh autoencoder using efficient spatially varying kernels. So Yi Zhou, I will leave the audience with you.
Okay, thanks for inviting me for this talk. And let me share the screen first. Oh, sorry, the host disabled the participant screen sharing. So it seems like sorry, I can do it. Hmm. Can you see the slides?
Yes.
Yes, we can see.
Cool, thanks. Yeah, so first a short introduction about me. Uh, I am E, and I am a research scientist at Adobe. I received my PhD degree from the University of Southern California under the supervision of Dr. Hao Li. And before that, I got my master's and bachelor's degree from Shanghai Jiao Tong University, working with Dr. Shuang Jiuxiao. And my research area mainly lies in digital human, basically everything about digital human, from human modeling to human animation. And so I conclude my work as creating autonomous 3D characters and finding the representation for deep learning for digital human. And here are some of my previous works. This one is about to reconstruct the full 3D hair from just one single image through a neural network. And this part is about generating complex and extended human motion. And related to that, this one is based on the skinning motion, which is the motion from the skeleton, how to generate the secondary motion, which is like this bouncing of the hair and the belly on the characters using deep learning, because traditionally people use simulator to generate this kind of secondary motion, but it is very slow and requires heavy computation. But in this work, we try to use deep learning to apply the secondary motion on 3D mesh. And these two are something related to today's talk, which is about how to use the deep learning architecture to reconstruct a human body, human hand, in with high resolution and high accuracy. And this is some example of having some of the 3D vision and the graphics technology in AR and VR systems. Okay, and today I will be focusing on this one. It is called the Fully Convolutional Mesh Autoencoder using spatially varying kernels. And it is a work that we published in NeurIPS in 2020. And this work was done during my internship at Facebook Reality Labs. And those people are my co-authors. Yeah, so uh, why would we want to do such a research? That is because when people are working on digital human or doing research in digital human, people will collect a lot of data about human body. For example, in this data, it's called the default. It's collected by MPI, and those people were collected by stereo systems to get multiple images of those people and reconstruct the 3D meshes of those people. And after getting the 3D meshes of those people, using a series of algorithms, we can process these meshes into the registered mesh. And what is registered mesh? Registered mesh are the meshes with the same number of vertices and connectivity. And why we would like to have them as registered? Because with registered mesh, it can be rigged on all the meshes can be rigged on the same skeleton, and they will have consistent texture UV, and also you can find the correspondences between the frames, so they are animatable, and you can apply texture on them. Um, and after we got all those registered mesh, then the question is, how could we find a low dimensional latent code, or let's say low dimensional representation, to so that from this low dimensional latent code we can reconstruct new 3D human bodies. So it will be, how can we get a generative model from train a generative model from these registered 3D data. Traditionally, what people do would be using PCA to do it, so that you can get a series of parameters, and from these parameters, you can get a 3D human body. But if you're doing this, it has some problems. The first one is, if you really compress the model into very low dimension, it will lose this method. I mean, PCA method will lose many details. And if you want to get high details, then your latent code should be very large. And that is the reason why in recent years, more and more people start to think about if we can use deep learning to get this latent code of 3D registered human body. Um, and that is why we want to think about how to design neural network on registered 3D meshes. However, in traditional neural networks, for example, the CNN architecture, it can not directly apply on 3D meshes. It usually can only apply on regular 2D structures. So how can we solve this problem? Sorry. One common practice, which I still see it in recent papers, is since we have very mature CNN technology on 2D image, why couldn't we just project the 3D mesh to 2D image? So in this school of method, people have this 3D mesh of human, and then through UV mapping, which is by cutting the mesh and deform the mesh, you can map the 3D mesh on a 2D uh, on a 2D grid, or as I said, on a 2D image. And in this image, each pixel correspond to a certain position on the human body. So the value of each pixel, instead of being RGB, is the XYZ of the position on the body, of a certain vertex on the body. And now we have the 2D image, then we can have a regular CNN to get the latent code and decode it and get the image again. And from the image, through UV mapping, we can get a final, we can reconstruct a 3D body from the UV image. However, this kind of method has many problems. The first problem is inherited from the way we do the UV mapping. Uh, so when we're doing the UV mapping, we have to cut the mesh, right? And then it introduces artifacts along the same lines, and also introduce artifacts from distortion. And here I show an example of the artifacts along the same lines. So along these lines, they are actually the cutting point of fingers on the image. And you can see that because of the discontinuity on those points, or let's say on those vertices, when reconstructing the color and the position, you can see the black holes here. And the second problem is through experiments, we found that if we're doing this kind of autoencoder, the network can learn the local features. For example, the local structure on the surface. However, it has very poor performance when trying to reconstruct some global deformation. For example, if the human has big deformation on the arm, like lifting the arm, putting down the arm, then this kind of structure has very poor performance. Then then what we want to do is to apply CNN directly on mesh so that we don't have the problem of UV mapping, the distortion, the artifacts along the seam, and it will be an elegant method that directly apply on mesh. But doing this, we will face several challenges. The first challenge is we cannot just sample uniform kernels on a non-uniform mesh. So let's see, in a regular 2D, or you can also imagine it to be a 3D, but anyway, in a regular CNN, it expects the connectivity and the structure of the grid, or let's say the graph, to be consistent everywhere on the grid. So we can say it is a shifting variance grid. And in that way, you can define a kernel with certain amount of weights for each local patch. However, on a mesh, the local structure shift a variant. So it means that for each local patch, the number of vertices can be different. And even you define kind of process the mesh so that you force that each local vertex has, for example, 6 vertices of neighbors for each of the local region, you still have the problem that the direction and the distance between one vertex and between the neighbor and the center are different. So even though you force the neighbor number to be the same, you can still not using the same convolutional kernel. And maybe someone will say, then let's define an operation that can ignore the density of the neighbors. For example, if can we just aggregate the features of the neighbors by just doing a mean operation? You can do that, but it will lose information. For example, if the center the center vertex get the mean feature of its neighbors, later, if you want to reconstruct the neighbors from the center, you actually don't know what is the distance and what are the directions of these neighbors. And so does any other isotropic operation. And recent years, there are many papers talking about how to define CNN network for graphs or for meshes. And I listed them here. So one school of method used the spectral. I call them spectral method. They use kernels like they map the features to the spectrum space and use kernels like Chebyshev. However, this kind of method, if you do experiments to train an autoencoder on them, you can see that sometimes they lose fidelity and sometimes the training is not stable. And there are also a bigger group of works that use feature conditioned method, like GAT, MoNet, FeastNet, and in conclusion, these methods they try to predict the weight of each edge through the feature on each edge. However, this type of method they are sensitive to big variations, and if and some of them are even isotropic operations, so that they cannot be used to reconstruct the geometry. However, they might be able to reconstruct some static local features such as the segmentation or the color. And there are some other methods, I call them special methods. For example, the spiral CNN. Basically, they say that, okay, let's define the kernel in an untraditional way. We define it as a spiral around centered from the center vertices. And this method is kind of a little bit ad hoc and it is limited just to 2D manifold. If the mesh is not a 2D manifold, then it cannot work. And there are also methods called it calls itself mesh CNN, and the operation is called edge CNN. This method, the good thing about this method is it can reconstruct the 3D geometry and it can handle not only registered mesh but unregistered mesh. However, when we did experiments using this kind of method, we found that it's very slow and it is also limited to 2D manifold. And if you use it, you can see it will. If you use it to reconstruct high resolution 3D meshes, you will see that some of the geometry information also loses. And then, secondly, for designing a mesh autoencoder, it's not only about to design the operation, the convolution operation. It also involves the designing of up and downsampling the mesh. In order to up and downsampling the mesh, in this kind of papers, they use method called quadric mesh simplification. And basically, so from the whole training data set, they first pick one of them as the template, and based on the template, they did the quadric mesh simplification and get the weight for that specific template and apply this weight for doing the mesh upsampling and the downsampling for the whole training set. So you can see that this method is overfitted to just one template mesh. And there are also more flexible methods like in Mesh CNN. They use dynamic edge collapsing. Basically, it's still similar. It's an algorithm that's similar to quadric mesh simplification. The difference is that instead of just using the distance between two vertices for the metric simplification, they use the features along the edge to do the simplification. But the problem is it's very slow and it's also limited to 2D manifold, and it is a minimal downscaling size requirement so that you cannot compress your mesh to as sparse as possible. And after talking about the existing method, our method compared to previous method, has high reconstruction accuracy and high generalizability because it doesn't depend on one template for the up and down sampling. And more importantly, it provides natural analogs of 2D operations in CNN, like the stride, the receptive field, the pooling, the unpooling. All these concepts that exist in 2D CNNs exist in our designed CNN for mesh. And oh, it's already 20 minutes. Let's accelerate. So our idea is actually simple. If you observe a mesh model, we can get the following assumption. So a mesh is actually a discretization of continuous space. And a continuous kernel can be shared in a continuous space. So in that sense, a discretized kernel can be sampled from a continuous kernel. So what does that mean? It means that our core idea is we can, in order to apply traditional convolution operation to irregular mesh, we can first imagine a certain structure of convolution kernel, for example, like this one. And then what we want to do is, if we want to apply this kernel on an irregular local patch, what we need to do is just to do a linear interpolation of all these all these weights on this regular structure. Yes, so the core idea is sample weight from a shared uniform kernel and then learn the sampling coefficients for each local patch. And then for a specific convolution operation, what we do is, for example, in this picture, these are the input vertices, and they are connected by these edges. And for an output Y, it is integration of the features of those connected X multiplied by the weight on each of these edges. And then the question is, how can we get the weight? So first, for each convolutional layer, we can define a set of weight bases. And then for each of the edge, we should have a set of coefficients. We call it A here, so that with those coefficients, we can interpolate the weight basis and to finally get the weight for each of the edge, and use this to do the final convolution operation. You can ask questions when I'm doing the talk if there's any part that you feel confused. Okay, let's continue. And then for the pooling operation, we will do something similar. So traditionally, people just compute the mean value or the max value or the minimal value of a local patch as the pooling output. However, on a mesh, we say that the local density is actually non-uniform, so we cannot just treat each neighbor vertices as the same with the same weight. Then what shall we do is we can do a Monte Carlo integration with learned density coefficients, which means similarly for each local vertex J, we can also learn the density coefficients for each of the edge, and then integrate all the values by those coefficients. And those coefficients are also trainable parameters during the training. And those parameters are shared across the dataset. And finally, about the scaling scheme, since maybe we don't have enough time here, so I will skip the details. But briefly speaking, given original graph
We
for
have other 30 minutes, so you can take other at least 20 minutes. You can still take it.
oh, okay, thank you. Right, then I'll talk about the scaling scheme. So given the original graph, remember that there are other papers do a quadric upsampling and downsampling, but that might not be the ideal way to do it because it depends on the XYZ value of a template mesh. So in our scaling scheme, we say that we don't want it to depend on the XYZ value of the vertices, but we only want it to depend on the structure of the mesh. So what we do is, here is an original graph. We say we should suppose the sampling stride is 1. Then it means that we will select a subset of sampled vertices so that their one-ring neighbors are not selected. And after selecting those vertices, you can see a graph. You can see the output graph like this, and we get the new connectivity of this output graph based on its connectivity based on the connectivity on the original graph. And then suppose for a convolutional or a pooling operation, the kernel radius is 1. We define the edge between the output and the input based on the one ring neighbor in the original graph. And if, for example, the radius 2, then we will get even larger region of vertices connected to the output vertex. And the reverse process is the same. So from pooling or convolution layer, we can get its dual unpooling operation here. And the unpooling operation has the same number of input vertices as the output vertices in its dual operation in the pooling layer, but it can have different radius to its dual operation. So that we can define convolution layer, pooling layer, transpose convolution layer, and unpooling layers with arbitrary stride size and radius size. And here I list those operations analog to regular CNN. So yeah, you can see that we can have convolution, transpose convolution, pooling, unpooling layers with attributes like a stride, kernel radius, basis size. Basis size is something we introduced, and which means the density of the basis in our with our imaginal grid, and the in-channel size, the out-channel size, the dilation, the stride. So it's basically everything you can find in a traditional CNN. And we also define the down residual and up residual layer, which is basically the same as residual layer in traditional CNN, which has the input to the which has the convolution and the transpose convolution layer added with the linear transformation, followed by some pooling and unpooling layer. Okay, now we have all our operation. Then what with those operation layers, we can design our fully convolutional architecture. So in this graph, I showed an autoencoder on a 3D human mesh. And in this autoencoder, we have 4 layers of encoder to encode the original mesh with roughly 7,000 vertices to just 7 vertices. And then have another 4 layers to decode it back to the original mesh. And interesting thing to see here is that those vertices, they are latent vertices at the middle layer. They are actually manually selected so that they kind of they are defined on the how to say the center of each part of the human body. So as I haven't mentioned in the up and down, in the pulling and unpulling layers is those vertices you can either choose it by our algorithm or you can also manually pick up those vertices. And that will give you very interesting applications, which I will show in the later slides. And one advantage of our method is by defining our network in this way, our method has a localized latent feature, which means here I visualize the receptive field of each latent vertex in the middle layer, and you can see that their influence on the human body smoothly propagate from the latent vertex. However, if you use method like quadric mesh simplification, the middle layer, the vertices on the middle layer looks like this, and they don't have this smoothly propagated feature. And as a result, this autoencoder with a compression rate at the middle, at the bottleneck, has a high reconstruction accuracy. And the middle is our method, and on the right side is the method called the Neural 3D-MM, which used the spiral CNN kernel. And here I visualized the reconstruction accuracy more with the comparison of more methods like the neural CDMM, the spectral method, the MONAD, the FeastNet. And you can see that our method has the lowest reconstruction error on the default testing dataset. Here are some quantitative results, and let's skip that. And compared to other methods that can only applied on 2D manifold, our method, because it doesn't have an assumption on the structure of the mesh, we can work for all types of mesh. For example, in this one, the dragon here is tetrahedron mesh, and on the left side is the ground truth. Those ground truths are generated by a simulator, and on the right side is our output. And this autoencoder encoded the sequence of the tetrahedron simulation. And another example is the reconstruction results on a non-manifold mesh. And the left is the ground truth, the right part is the output. And for non-manifold mesh, you can see that, for example, if I zoom in the local structure, you can see that, for example, this part is non-manifold, and this part, the spike here, it's also non-manifold, but the network can still handle it. And the ground truth data is also generated by a simulator. And For very high resolution meshes, for example, meshes with 150,000 vertices per mesh, we still have very good reconstruction results, like here. And those models are captured from Facebook Reality Lab. And on the right side is some results for human hand. And in this experiments, we not only reconstruct the XYZ position of the vertices, but also the color of the vertices. Now, then is the fun part. So I earlier mentioned that with our architecture, we can have those localized latent space. And with localized latent space, we can do a localized interpolation. Traditionally, if you have a latent space for the global feature of the mesh, when you interpolate the two latent code, you can get the interpolation between the two global shape. However, in our case, we can do a local interpolation. Like here, for example, from man A, we get those 1, 2, 3, 4, 5, those 5 latent codes for this part of the body, and for man B, we get this part of the latent code. And then we reconstruct a new man A with those blue latent code and plus the red latent code. And now the result is this new man A got all the other parts of the body the same as the man A, but his right leg raised up like man B. And what's more interesting is this new man A's left leg, although it has the same pose as man B, it is much thicker than man B's left leg. And this thicker right leg, the thickness of the right leg is similar to the thickness of man A's left leg, sorry. And another result about this is, for example, on the human hand experiment, I defined the latent vertices on the tip of each finger and one on the wrist as well. And then I did an interesting interpolation. So suppose this one is the source and this one is the target. In this experiment, I tried to interpolate only one of these latent codes. For example, here, this one is the middle finger, this is the index finger, and this little finger, and this one is the interpolation for the whole hand. And you can see that doing this type of interpolation, only the finger or the wrist that we specified are interpolated, but the other part of the hand remains the same. And in this way, we have much higher power. We have a more powerful interpolation tool for generating different hand gestures with different hand shape. And finally, I'd like to talk about the limitation and the future works. So I draw this axis. The horizontal line is the reconstruction accuracy. The vertical line is the flexibility. So the lowest part is fixed connectivity and the surface mesh or the 2D manifold mesh. And so here means the network can only apply it on registered mesh with fixed connectivity, and it can only apply it on 2D manifold. And those two methods lies in this part. With a little bit more flexibility, it can apply on arbitrary graph, but with fixed connectivity. is our method with high reconstruction accuracy. And there are also methods with even more flexibility, like unfixed connectivity, but only apply on the surface mesh, which is the edge CNN. Uh, and finally, the most flexible one is the unfixed connectivity with arbitrary graph, which are those big group of methods called graph CNN. However, they usually can only reconstruct local features, but not the 3D geometry, and they cannot for example, applied on up and downsampled architecture. I mean, architecture with upsampling and downsampling of the mesh. Okay, so the future work is obvious, lies here. So can we design a convolutional neural network on graph that has both high flexibility and high reconstruction accuracy? And I think this still is a unsolved problem, but will be very interesting to see if there will be future works working on this. Okay, so that is my talk, and you can find the code of the method here, and this is the project page. And now, any questions?
Yeah, thank you, Yi, for the very nice talk. It was indeed very impressive. So if anyone have questions, you can either unmute yourself and ask directly your question, or you can type your question in the chat in this Zoom application, and I can read the question for you. So maybe I will start since I have a couple of questions. So first, Yi, so you have showed that your model actually can work with, say, a relative small number of vertices and also an example of a higher number of vertices. Have you compared like in terms of the complexity or the computational time, how these grows against the number of vertices that you have in the model? In case, is that possible to apply that to even a larger model, for example, for 1 million or more than that number of points?
Oh, that's a very good question. So, um, I think so we should think about it in two ways. The first is how much memory we need to use for training. And the second part is how long it needs to do the training. I think for how long it needs to do the training, it actually the resolution doesn't matter that much. Actually, the variance, the complexity of the whole data set, the size of the data set matters more for the training time. And then for the size of the or the resolution of the mesh, it will affect the memory cost of your training. So, for example, I kind of remember um, for 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 network trained on this one with 150,000 vertices, it used I remember like 16 gigabytes of memory during training, and for a batch size, sorry, I cannot remember exactly, but when we train it, we use a GPU. We use a GPU memory of 16 gigabytes, and for the training of the size of like this one, or roughly recently I had a training with roughly 10,000 vertices, and with a batch size of 8, and it cost the memories of roughly 4 to 5 gigabytes. So it's acceptable. And for the inference, because everything, if you check our code, you'll find everything that computed in parallel. So the inference time is super fast, just like traditional 2D CNN.
You mean the application, online application is very fast, right?
Oh, yes.
Thanks. But you mentioned that so that it actually depends on the variance of the data. So just wondering, you present something which is more complicated than, for example, people project that to 2D space, etc. Will that make you need more data to converge your training, or it's somehow comparable to the previous methods?
Oh, so if you just compare with methods like, yeah, this one, it actually, the mesh CNN converge much faster than this one, and it actually converges very fast. If you want to train on the default data set, if you are familiar with this one, which is, yeah, this, or actually it's the, let me find yeah. So if training on this data set called the default, it contains, oh, sorry, I don't remember how many meshes in total, but a lot of meshes and a lot of different identities. It actually, to get a rough human body shape, it only need 1 hour of training. And for the network to converge to a very high accuracy, I remember I used 1 or 2 days for the training. So actually, the network converged pretty fast.
Thank you. And I see there's a hands up for Ursula. So Ursula, would you please ask the question?
Yeah, thank you. Brilliant talk. Thank you very much. And I was just wondering if during the dynamic, for example, in the video that you were showing, is the number of vertices fixed at all time, or it can
Yes,
be? Okay. Do you
yes.
think that in a case of having a different number of vertices for the time series, can you still adjust your method, your code to this situation, let's say?
Oh, that's a very good question. Actually, I have been thinking about this for 2 years, and I don't have a perfect solution for it because designing a CNN that can work on unfixed structure meshes, I think is a super hard problem. But one complementary way, which is also applied in our recent paper, is for simulation. So, I mean, just for the case of simulation, in order to handle different type of meshes, we can actually create a cage around the mesh so that at least for that cage, each local patch look the same, and in that way we apply a static CNN kernel on each of the local patch of that cage, that 3D cage, instead of directly on the 3D surface, and in that way we can, and then the 3D cage will drive the motion of the mesh inside it, and in that way we kind of map the irregular mesh to a regular mesh, and to handle different topology of meshes, but it still doesn't completely solve this method of how to apply CNN on unfixed structure of meshes directly.
Okay, thank you.
Thank you, Yi. I see there are also questions from Jake in the chat. So Jake, would you like to unmute yourself, or you'd like me to read your questions? Okay, I think I will just, yeah, okay, I'll just go and read it. So the question is, what frameworks were used while implementing this project?
Oh, we implemented by PyTorch. Yeah, so if you want to run our code, you just need to you just need to install PyTorch.
I think you put your link on the GitHub as well
Yes.
on your page. Okay. And then we have also a question from Isaac. So the same is that, do you want me to read your questions, or you want to ask it yourself?
I don't mind asking. Hi.
Yeah, please go on.
I really enjoyed that talk. Thank you so much. That's super interesting. I don't come from a background of like mesh CNN stuff, but my group, we do lots of kind of voxelized 3D volume stuff with GANs. And what I was really interested in is when you showed your kind of the output of your generator, of your encoder network, with the kind of like accuracy mapped onto the mesh, there were some regions which were quite red, whereas most of it was blue, and you had kind of hotspots of inaccuracy. I was wondering what you think is significant about those areas and why the network struggles with those kind of features in particular.
Oh, I think that's also a very good question. So basically, from all my observation, I think this 3D CNN we designed, it actually works pretty like a 2D CNN on 2D images. So the drawbacks of 2D autoencoder also is the drawback of a 3D autoencoder, which is it might lose some high frequency details. So for example, if you train a 2D CNN autoencoder on a 2D image, the results, if your latent space is too small, then the output image will be kind of blurred. And similar to the, the our mesh CNN, if the latent code is too small, and if you don't apply residual layer to it, I mean the residual block to it, then the output will lose some of the high frequency details. And in order to to improve the accuracy at those regions, there are two ways. The first way is just increasing the latent code size. And the second way, maybe smarter, is to first try to map the original data to high frequency space and low frequency space and learn them separately.
Great, thank you.
I see also there's a question from Claire. So Claire, do you want to ask your question, please?
Hi, thanks, Sibo. Yi, that was a really nice talk. Thank you very much. I'm not sure whether I'm going to be able to ask this question very clearly, but say for the person, you had a person where you defined 7 points, I think, on their body, and you compressed the information down to those 7 points. And you said you defined those points manually. Did you try compressing down to 7 points, but not specifying where they should be, and then comparing the result?
Yeah, very good question. So, yes, if you don't manually specify in the middle layer which points do I want, actually the algorithm is actually a breadth first searching algorithm. Will just randomly pick those, not that randomly, but sort of randomly picked those vertices, so that those latent vertices at the middle layer, it might not be 7, it may be 6. Actually, I have did that kind of experiments. I remember if I don't specify, there will be 6 vertices, and although they kind of still distributed evenly on the body, but they might not be exactly what we want, what we would like to see. So in terms of that, I found that the reconstruction error actually doesn't change much, but it will lose this nice receptive field distribution, so that when we want to do that fun part of interpolation, it won't work that well. Yeah, so in terms of reconstruction, if you don't need anything like doing localized interpolation, actually you don't really need to manually define the vertices. You can just let the algorithm run and pick the vertices for you.
Great, that's really interesting. Thanks very much.
Thank you.
Thanks, Claire, for the question, and thank you, Yi, for the answer. Is there anyone have still, let me check, probably a final question for today? We have still got 3 minutes. So if nobody has another question, in fact, I still have one, so I may take this chance. And so if I understand well here, so what you present is the reconstruction of the latent space. So you compress that and you decompress that to the full space. I was wondering, so now many people did, for example, in the CFD to use some kind of the recurrent neural network, such as the LSTM, to learn the dynamics of the of objects inside the latent space. Do you think your method can be easily incorporated with that method, with the, for example, the recurrent neural network surrogate model, to somehow not only like reconstruction, but also to predict the people movements if we can show him many videos in the full space?
Oh, actually, I think it will be a very interesting application, because in this case, it's actually a sequence of of animation, right? And so in this case, actually, the network, the autoencoder, encode all these vertices. So actually, it's the vertices on the cage, or let's say this volumetric mesh, to just two latent vertices. So it compressed it to be two latent vertices. So I can imagine in the application you said, you can first compress your whole mesh to your latent vertices and apply your LSTM or RNN structure on those latent vertices and predict the next frame's latent vertex, and then decode them back to the original mesh. It will be much faster than just directly apply your LSTM on the whole
full space.
Yeah, the full space.
Okay, thank you. Thank you very much for that. So if nobody else has the question, so I think we can close our talk today. So thank you again, Yi, for the very nice talk, and thank you everyone for attending. I see there's, okay, yeah, it's fine, it's not a question. So thank you for people for joining us. And yeah, hopefully we can meet in person later after the pandemic is over. And yeah, very nice evening then to everyone here in Europe and in the UK. And nice day to Yi. Thank you again for accepting our invitation.
Thank you guys. Good evening. Bye-bye.
Bye.